Happy Monday, everybody. I am so sorry I neglected to tell you that I'm in a conference in LA until Wednesday. So I'm just going to make you some videos outlining what should have happened last week. So firstly, let me apologize for that. My master sheet went missing, and that made it very difficult for me to teach you this glycolysis. So yeah, I'll be back Wednesday afternoon, and I can meet with you guys. I will work with your schedules, whatever time you need, and I will be available to you all weekend. So just let me know. And right now I'm just going to start you off with some one molecule glycolysis, okay? So let's start right here. We have our 6 carbon glucose that for the sake of this we're going to have going into a hepatocyte, as we can see based on this GLUT2 transporter. This could also be in the pancreas, I suppose. But this 6 carbon glucose is going to come inside of our cell. So here, let me grab a pen. This is my cell membrane. This is my membrane transporter for glucose. Okay, so glucose is going to come into the cell, and then right away it's going to have this interaction with a family of kinases called hexokinases, and hexo means 6. So these 6 carbon sugars are going to interact with this enzyme that's meant to act on a 6 carbon sugar, and that's going to phosphorylate this 6 carbon chain, okay? And that's to help keep the glucose within the actual cell itself. Hexokinases 1, 2, and 3 have a negative feedback loop to basically stop them from making too much of G6P, this glucose 6 phosphate. So 1, 2, 3, 4, 5, 6 carbons, and on my 6 carbon I have 1 phosphoryl group. So my glucose 6 phosphate will actually come back when there's a high enough concentration and cause a negative feedback loop, which will block out hexokinase. And that's just to keep our cells from accumulating too much G6P within them. And then we have a hexokinase 4, which is never turned off. And that basically means that we always have a constant influx of this G6P into our cells, so that they're basically to keep up with the housekeeping demands. So we always have a base level of metabolism that's going on. And so bringing this back, our 6 carbon has been phosphorylated by a hexokinase, and it's a kinase, right? So it requires 1 ATP for energy. We can see that here, minus 1 ATP. And that is basically making a glucose 6 phosphate, okay? And what glucose 6 phosphate, this is a molecule of sugar here. And traditionally there would be a hydroxyl group on this 6th carbon here. But what we see is that we've got this kind of Y shape here, and then this hexagonal carbon ring structure with an oxygen in the middle of it. And off of these carbons, which I've numbered here, are little hydroxyl groups, okay? And what we see here is that we can number these. So this little 6 carbon ring, 1, 2, 3, 4, 5, 6 carbons. And then on the end of that 6th carbon, we have my phosphoryl group, okay? And that's where my glucose 6, so that means 6th carbon, phosphate comes from, okay? So my G6P is still in the cytosol. It's floating around, and it's going to start interacting with my next enzyme, okay? And in this case, it's phosphoglucoisomerase, okay? And so basically what the isomerase nomenclature means is that we're not actually changing the chemical structure of this molecule, we're just changing the location of some of its parts. And so what phosphoglucoisomerase, PGI, is going to do is it's going to come down here and it's going to open up this carbon ring structure a little bit, okay? I'm not going to change anything. I'm basically just going to pop an arm out off the side, okay? And so we still have just a 6 carbon sugar, as we can see in this simplified diagram, with a phosphate group on the 6th carbon, okay? And what that looks like after the phosphoglucoisomerase has acted on that glucose is that we have this 5-sided group, okay? So a pentagon has been formed. And on the right arm here, if we're pretending that he's looking at me or it's looking at me, we have a phosphate group, okay? And on the left-hand arm here, we can see that there's a hydroxyl. So it's almost like this little hexagon or pentagon, has grown 2 little arms off the side, okay? So it's like a fan cheering in a stadium, okay? And so what we see is that this is actually setting us up to break down into 2 3-carbon chunks, okay? So we have 1, 2, 3 carbons here, and then 1, 2, 3 carbons here. So we have 2 little lines of carbon here that will eventually split right down the middle here, okay? And so this is my fructose 6-phosphate, okay? So when I have this pentagonal shape here with one arm off to the side and one arm off to the side, this is my fructose, okay? And on the 6th carbon, we still have that phosphate group, okay? So we didn't actually move the phosphate group. We just opened up that from that hexagonal shape here to a pentagonal shape here, okay? As a result of that phosphoglucoisomerase, okay? And then we're still floating around on the cytosol, so this is easily associated. This F6P is floating around, and it becomes entrapped by this phosphofructokinase, okay? And this phosphofructokinase, as its name implies, is a kinase, so we're going to add another phosphoryl group, okay? And so going from this shape here, we're basically going to throw, sorry, my camera's having a hard time focusing. We're basically going to throw another phosphoryl group, so one of these, on this hydroxyl group right here on this first carbon. Okay, and so now we can go to that simplified view. So we've got 1, 2, 3, 4, 5, 6 carbons. So on my first carbon, I've got a phosphoryl group, and on my 6th carbon, I've got a phosphoryl group, and that's going to make me my fructose because it's still in this shape, this pentagonal shape. It's a fructose 1,6 biphosphate, F16BP. Fructose 1,6, so first and 6th carbon biphosphate, 2 phosphate groups. Okay, so now when we're looking at this molecule, basically we've got, you know, our cheerleader with 2 pom-poms, okay? So we've got a 3-carbon group here, we've got one arm up in the air waving our phosphoryl group around, we've got a 3-carbon group over here with another phosphoryl group waving around. So it's like our little cheerleader for glycolysis that's waving these around in the air and saying, yay, we're making energy. That's my bad representation of that. All right, and so to give you another simplified view of this, basically we have 2 little 3-carbon groups that are bonded together, and they've got their little phosphate group. And that's going to look very familiar because that's basically what our final substrate from this one molecule glycolysis is going to be, our glyceraldehyde 3-phosphate. So we can see how that's very similar here. Okay, so what we're getting out of this, we still have this single molecule. Now we have to cut it down the middle, okay? And we're going to do that with fructose 1,6 biphosphate aldolase. So my aldolase is going to basically cut this down the middle and leave me with 2 3-carbon groups, but they are sadly not equal. Okay, firstly, we're going to make a glyceraldehyde 3-phosphate, my G3P, which is what we want, which is what we're going to run into our next steps. But also what we're going to make is a dihydroxyacetone phosphate, okay? And so basically that's as a result of this oxygen group here that gets cleaved off onto this side, onto this right side, and then that comes up and forms a dihydroxyacetone phosphate, okay? And it's very, very similar to G3P, but it's not quite similar, so we have to use another isomerase to kind of change the shape. And what we're going to do for that is we're going to use triose phosphate isomerase, okay? And that is going to leave me, you can see how this arrow is basically swinging back around, that's going to make me another glyceraldehyde 3-phosphate. And so at the end of this, we've got 2 of those, okay? So that's basically the cleavage point where we go from one molecule glycolysis, where basically for one molecule of glucose, all the substrates we list here, we're going to get one of them for one molecule of glucose. And then we're going to move into the 2-molecule glycolysis that will feed us into the Krebs cycle. Okay, and so what we can see here, so coming back to this, remember that whenever I see a kinase, it's going to cost energy to use that phosphorylating feature. So we basically take an ATP and we run that into our kinase, and that is where we're getting this phosphoryl group. Okay, so remember that ATP is adenosine triphosphate, and we're going to basically cut the tri and make it a di, so from 3 to 2, and we're going to transfer that phosphoryl group onto our glucose. So we do that twice, right? We have our hexokinase, our first step, our hexokinases 1, 2, 3, and also 4. And that's going to phosphorylate our glucose. So that's going to cost 1 ATP, so that's minus 1 ATP. And then we have our phosphofructokinase, okay? And remember, that's taking my fructose 6-phosphate, and that's adding another phosphate on it so that I get a fructose biphosphate. So overarchingly, for one molecule of glucose, in this first step for the one molecule glycolysis, we're losing 2 ATP, but we're making 2 G3 Ps. Okay, so my glyceraldehyde 3-phosphate. And I know it's hard to get all these little acronyms down, but you'll pick them up really quick. Just make sure that you're drawing out this entire system a couple of times, and it'll come really quick and it won't be any problem. So here's our overall look at this procedure. My camera will focus, maybe. And there you go. Email me if you have any questions. That's our one molecule glycolysis.